Hello, class 12. The topic that we are going to discuss today, or the circuit, alternating current circuit that we are going to look at today, is the LCR circuit. So to say, it's a combination of the inductor, the capacitor, and the resistor in series, and the combination of these three components is connected to, of course, an alternating power source. V is V0 sine omega t. Now we have seen that XL is the inductive reactance, which is equal to omega L, which can also be written as 2 pi f into L, where F is the frequency of the alternating current. And likewise, the capacitive reactance XC is 1 upon omega C, which is 1 upon 2 pi f into L. Now, at any instant, say, current is flowing in the clockwise sense. Current I is flowing in the clockwise sense. I is the instantaneous value of the current. Alright? So, this inductance, so to say, is going to offer some resistance to the current, which is of course equal to this much. Alright? And thereby there will be a potential difference across the inductor. The potential difference across the inductor, let's say, is VL, which is I into XL. Likewise, there will be potential difference across the capacitor, which is IXC, or VC, which is I upon omega C. And of course, there will be a potential difference across the resistance, which is VR, which is I into R. Now, what we do is, if we draw a phasor diagram for this circuit and try to understand the phasor diagram clearly. Now, if the horizontal line represents the direction of the current. Now, we've already studied that in case of a purely resistive circuit, the potential and the current, they are in the same direction, or so to say, they are in phase. So if this is the direction of the current, then the potential difference across the resistance, that is VR, will be in phase with the current, that is the direction of VR will be the same as that of the current. And we know that in case of a purely inductive circuit, the potential difference VL across the inductor leads the current by a phase angle of pi by 2. So if this is the direction of current, then VL will be in this direction, because it is leading the current by a phase angle of pi by 2. And for a purely capacitive circuit, we've seen that the current leads the voltage by a phase angle of pi by 2. Or so to say, the voltage lags behind the current by a phase angle of pi by 2 in case of a purely capacitive circuit. So, this is your VC, which is lagging behind the current by a phase angle of pi by 2, as you can see. Now, since this is a phasor diagram, so to say, all of these components, VR, VC, VL, they are vectors. So therefore, the rule of vector addition applies to these vectors. If this is VC and VL and VC, they being in opposite direction, if I subtract this length from here, so a new vector, this vector over here, alright. So this vector over here is VL, or let me rather write, instead of a minus sign, VL, this is a tilde actually, okay. So this sign VL, I don't know why, but I like reading this sign as a quack, okay. I don't know, I feel it's like a duck. Okay, so VL quack VC. VL quack VC means between these two, VL and VC, its meaning is more important, okay, rather than its name. So between these two terms, the sign tells us whichever is greater, okay, that subtracts the other one. So if VL is greater than VC, this symbol means this is VL minus VC. Whereas if VC is greater than VL, this symbol means VC minus VL, remember that. Okay, so meaning of this quack. Alright, so VL quack VC means VL minus VC. if VL is greater than VC, and VC minus VL if VC is greater than VL. So do not forget that. Okay. So here we've considered VL is greater than VC here in our case. Therefore, this is VL minus VC, so to say this vector over here is VL minus VC. Now, therefore, we have to deal with two vectors, so to say, therefore, which is VR and VL quack VC or VL minus VC. Now, these two are vectors starting from the same point, as you can see. So, obviously, we are going to apply something called parallelogram rule to these two vectors. And the parallelogram rule of vector addition tells us that the diagonals of the parallelogram starting from the same point gives us the resultant. So if this is your parallelogram, imaginary parallelogram, then the resultant of these two vectors is here. So this is the resultant. Let's call the resultant capital V. V is your resultant. So what do we write? So V, or rather the magnitude of V, is square root of VR squared plus VL quack VC whole squared. Alright, now we can substitute their values from here, or V is equal to square root of, so this will be I into R whole squared into I into XL minus I into XC whole squared. So what we can do is we can take out I squared common, so this becomes R squared from here, plus, see this is a square bracket, plus XL minus XC whole squared. Okay, XL quack XC whole squared. Whichever is greater between the two, that will subtract the smaller one. Okay, so we've reached here. So I think I can erase this part, which of course I'm doing. So what therefore we get is I squared can be taken out of the square root of course. So V becomes I into the thing inside the square root, which is R squared plus XL quack XC whole squared. So to say, potential is current into something inside the square root. Now this something inside the square root is denoted by a capital Z, and this Z is equal to R squared plus XL quack XC whole squared, and this Z has a name, it's called impedance of the circuit. It's called impedance of the circuit. Now what is this impedance of the circuit? Impedance is the effective or total resistance that is offered to the flow of alternating current due to these three components. The individual resistance offered by an inductor is called inductive reactance. The individual resistance offered by a capacitor to the flow of alternating current is called it's called capacitive reactance. So the total or effective resistance offered by these three components together to the flow of alternating current is what is called impedance of the circuit. So impedance therefore is the effective resistance, remember. Okay, so from here therefore we can write V is I into Z. So this is in the form of Ohm's law, as you can see written. Potential is current into the effective resistance of the circuit. Is this okay? Alright, so don't forget, this is something called the impedance. Let me erase this part. Let me not erase the phasor diagram. Now, we also see, if say for example, this angle is phi, the angle between the effective potential in LCR circuit and the current is phi. Okay, so from that, or from this phasor diagram, we can write tan of phi is equal to perpendicular by base. Perpendicular is VL quack VC, so VL quack VC divided by VR. Okay, or this can also be written as, or tan phi is, so I can take out I common from both of these two terms. Here also I can take out common, so they divide each other out. So this becomes XL quack XC divided by capital R. Alright, so what is phi therefore? Phi is tan inverse of XL quack XC divided by R. So this is your, I hope you all can understand. Let me erase this part here. So let me write phi is equal to tan inverse XL quack XC divided by R. So phi is the phase angle, so to say, between the effective voltage and the current in LCR circuit. Now we need to draw some conclusions out of it. So let me erase this part only here. So see, what are the conclusions that can be drawn? The conclusion that can be drawn is, number one, is if XL is greater than XC, or so to say, this means VL is greater than VC, the thing that we have considered over here. So if the potential across the inductor is greater than the potential across the capacitor, or so to say XL is greater than XC, then what happens is we see that, like in this phasor diagram, the voltage leads the current by a phase angle of phi. Okay, so to say, the circuit on the whole, if VL is greater than VC, acts as an inductive circuit, because what happens in an inductive circuit? The voltage leads the current by whatever phase angle. Okay, if it's a purely inductive circuit, it leads the current by a phase angle of pi by 2. We know that. Okay, so if VL is greater than VC, since voltage leads the current by some phase angle phi, so therefore, if this is the case, the circuit acts as an inductive circuit. Acts as an inductive circuit. The board is smaller. Okay? Not smaller, the board is small for me to write here. So, number two, what happens if XC is greater than XL, or so to say, the potential across the capacitor is greater than the potential across the inductor. So in that case, VL quack VC, or so to say, VC minus VL will be in this direction, and a resultant will be somewhere over here. The same picture, exactly reversed, mirror image of this, so to say. Understood? So in that case, what happens? The potential will be somewhere over here, potential V will be somewhere over here, and this will be the phase angle. So to say, if VC is greater than VL, the voltage lags behind the current by a phase angle of phi. Or in other words, the whole circuit starts acting like a capacitive circuit. So if this is the case, then the circuit acts as a capacitive circuit. Acts as a capacitive circuit. Okay. Alright, so these are two cases and we still need to deal with the third case. Let me erase this part here. Let's not erase the phasor diagram, it's important for us. Case 3, if XL is equal to XC, or for that matter, VL is equal to VC. Then what happens if this is the case? We've already seen the impedance. I'm rewriting the expression for the impedance over here. This is square root of R squared plus XL quack XC whole squared, of course. So the case we are considering over here is XL is equal to XC. So what happens to the second term over here? It becomes 0. And thereby, therefore, what happens to your impedance? Impedance simply becomes equal to R. So if the inductive reactance is equal to the capacitive reactance, we see that the effective resistance offered by the circuit, or so to say the impedance of the circuit, is equal to the resistance of the resistor itself. Or in other words, this circuit, LCR circuit, simply acts as a purely resistive circuit. In which case, of course, there is no phase difference between the voltage and the current. Do not forget that. Alright, so if this is the case, then voltage and current are in phase with respect to each other. Alright, you can make out from, the expression for tan phi also. Tan phi is XL quack XC divided by R. So if XL is equal to XC, then obviously the numerator is 0. So tan phi becomes 0, which means phi is 0. Okay, so there is no phase difference between the voltage and the current. So in this case, if this is the case, therefore the circuit acts as a purely resistive circuit. Purely resistive circuit. Alright, class 10. So do not forget these three cases, very, very important for you all. And especially this third case. This third case where the impedance of the circuit is equal to the resistance of the circuit, or where XL is equal to XC. This third case is called the case of resonance for LCR circuit. Okay, so from here, now I think I can erase the phasor diagram also. I believe you've already copied this. So let me do the conclusion part. So XL is equal to XC. This is a case of resonance. So what happens here is XL is omega L and XC is 1 upon omega C, or I can write omega squared is 1 upon LC, or omega is equal to 1 upon square root of LC. Now since omega is 2 pi f, omega is 2 pi f, so therefore f can be written as 1 by 2 pi square root of LC. So this is the frequency, so to say, of this circuit. Okay, so to say, this circuit also has a frequency of its own, depending on the value of the inductor and that of the capacitor. This circuit has a frequency. Okay, so the case of resonance is when the frequency of the circuit exactly matches with the frequency of the alternating current or alternating potential that is applied. Then what happens is, then only this case happens. Okay, the case of resonance occurs when the frequency of the external alternating current matches with the frequency of this circuit, remember. And we can see that the frequency of the circuit is dependent on the value of L and C. Okay, so do not forget this is a case of resonance, and this is all that we need to know about the LCR circuit. Okay, now actually the thing is, only if we had L and C in a circuit, what happens is, in an LC circuit, if we only have this, if we didn't have R component over here, then what would happen is, then what would happen is, if the capacitor is a charged capacitor, let me draw the capacity here, okay? If we have L and C in a circuit, then if this capacitor is charged, positive and negative, so in this circuit, there will be to and fro flow of current in an LC circuit. Okay, so because of this to and fro, so this to and fro movement of current in an LC circuit has its frequency of oscillation depending on the value of L and C, which will be equal to this. Understood? So wherever we have L and C in a circuit, that circuit will have a frequency of its own, and that frequency actually is the frequency of oscillation of current in this circuit. So if the frequency of the circuit, like I was saying, matches with the frequency of the alternating potential that is applied in our LCR circuit, then the case of resonance occurs. Okay, so this is all for LCR circuit. Thank you, plus 12.